Okay, so if there are no questions, let's get started. So I wanted to give you guys a couple of announcements. As you guys probably know, we started doing the quizzes online instead of in lecture. And because there was a pretty short notice about this and there were some problems that some students have, we're going to give you guys a second chance to do quiz 5. So you can, if you want to, you can redo quiz 5, but you need to do it before the start of lecture on Tuesday. And so the highest score of the 2 tries you have will be the score that you keep. And quiz 6 needs to be done by Tuesday before the start of lecture. So you need to do it at home before lecture starts. And again, it'll be short, 3 minutes. Yeah. That's right. That's correct. Yep. On waves. And again, you guys know that you have a homework due tonight, right? An article summary. And so you guys probably also noticed that we're not doing the peer reviews anymore. We had too much trouble with the system to make it work, so we're not going to do that anymore. So your final draft is due today. Yeah. Does anybody know? I actually don't know. It's 11:59. Yeah, but I wouldn't wait till the last minute. I would try to get it done, with plenty of time in case something happens. Okay. So last time, Bob talked a lot about sort of properties of waves. And what we're going to do today is we're going to talk about some characteristics of waves and some phenomena that you see in waves that you don't really see in other places. And so before we do that, I'd like to just do a quick review of some of the properties of the waves that we talked about. And so before we do that, what is a wave? Does anybody remember when we talked about waves, how did we define it? Well, we talked about a wave as sort of a disturbance, right? Something that moves through a medium. So for example, I can shake this rope and we see a wave traveling across it, even though each individual piece of the rope wasn't moving across. There was something that was moving across, and that's the wave. And then we talked a little bit about what are some properties of waves, right? And so one of the properties we talked about is the amplitude. And what is the amplitude of the wave? Yeah, it's the size of the disturbance. If we're talking about the wave on the rope, it's how high the rope moves up and down. Or if we're talking about a sound wave, it's sort of how big the pressure gets in the air. So this is the size. And how do you make the size bigger? Like if you have a wave, how do you make it increase the amplitude? Yeah. Well, so the amplitude is actually independent of the wavelength. And it's also independent of the speed, which we'll see and we'll talk about. But if you have a bigger disturbance, what does that mean in terms of energy? There's more energy, right? So this amplitude is really measuring how much energy the wave has, okay? And it actually goes as sort of the square of the amplitude, the amount of energy. Okay, and so since you brought up wavelength, let's talk about that. What is the wavelength of a wave? Yeah, exactly. So if I have a wave sort of traveling along and I take a photo of it so that it's sort of a snapshot in time, so it's only at one single time, I can sort of see a pattern that looks like this, right? Something like this. And if I measure the length of one of the cycles of these waves, that's the wavelength, right? So it's the length okay, and so what other properties did we talk about? Frequency, yeah. And what is frequency? Yeah, so you can think of it like if now instead of taking a snapshot, a photo, if I'm just standing in one place and these waves are passing me by, I can count how many of these wavelengths pass me in a given second, and that's going to tell me the frequency. It's telling me how many cycles pass by. Okay, and there's one more property that we talked about. Does anybody remember what that is? And it's related to the ones up here already, yeah. Yeah, the wave speed or wave velocity. And so when we have a wave, we see that it sort of, if we took a snapshot in one single photo in time, it looks like this. And if we took a time later, another photo, this picture would get shifted over a little bit, right? And it would keep getting shifted over as we move along in time. And so you would see this peak moving along. And if you measured how fast the peak moves, that tells you the wave speed. And does anybody remember how the wave speed is related to the frequency and the wavelength? So we take the length of a wave and we multiply it times the number of waves that pass us per second, and that gives us the speed. So we take the wavelength times the frequency. Okay, and so these are sort of the basic properties of waves, and we're going to sort of talk a little bit in detail of what they mean and what different things can happen when we have waves. And so to start out, I wanted to give you an example of a wave, and this is a sound wave. So let's see if I can get this going. Can you guys hear that? Yeah, okay, great. And so what's happening here is I have this signal generator. It's creating an electric signal that's going into this speaker. And inside the speaker, there's some coils. And this signal is sort of oscillating up and down, so the voltage is changing. And as the voltage changes, the current through these coils change, right? You guys remember this from last chapter. And so that changes the direction of the magnetic field. And that causes the speaker head to vibrate back and forth because it has a magnet attached to it. And so the speaker is vibrating back and forth. It's pushing the air in front of it that's vibrating back and forth, and that's sending the wave out to you guys. Now, what would happen if I had a knob here that turned up this electric signal and made the volume louder? What would happen? What would happen to the wave? The amplitude would go up, right? And you would see that as it sounding louder. And so right now, I've just turned on this speaker. What do you think is going to happen if I turn on two speakers? Do you think it's going to get louder? All right, well, let's see what happens. Raise your hands if you hear it louder. Okay, so raise your hand if you hear it louder. Who hears it louder? I'm going to need some class participation for this. So let's go back and forth. So here it is with just one, and here it is with two. Who hears it louder? Raise your hands. Guys, come on, I need to see everybody's hands. If I don't see hands, I'm going to make you stand up. Okay, so there are some people that hear it louder and some people that don't. What's happening? Is it that some people's ears just sort of stopped working because it's so early in the morning? Okay, so this is one of the sort of phenomena that I want to talk about. Try to understand why it is that some of you hear it louder and some of you don't. And so to understand this, let's first think about if these weren't waves, if instead of waves, let me turn this off because this is probably annoying you guys, right? So if instead of throwing waves at you guys, what if I had one of those baseball pitching machines and I was throwing baseballs at you, right? And so I'm throwing one baseball, I have one machine and I'm throwing baseballs at you. So the energy from this baseball machine, it's taking it and putting it into the baseball, the kinetic energy of the baseball, it's getting thrown and it's hitting you, right? And then that energy is getting transferred to you. So what's going to happen? You're going to feel that energy and it's going to hurt, right? But now what if I get two baseball machines and turn them on and aim them at you, right? So now you have baseballs hitting you twice as much. What's going to happen in terms of the energy that gets to you? It's going to be more, right? You're going to hurt more because you have more baseballs hitting you, right? And it doesn't matter if I turn it on so that the baseballs fire at the exact same time and hit you at the same time, or if I fire them so that they hit you separately. In either case, you're still getting hit by more baseballs, so it's still going to hurt. Now, this is not the case with waves. It really depends on the timing of the wave. And so let's see if I can draw this on the board. Okay, well, let's just start over. So say I'm over here and I'm emitting two waves. So one wave is like this, and one wave is like this. And it's going down, and I'm standing here trying to listen to these waves. So let's say they come in that this wave, whenever it reaches me, looks sort of like this. Okay? And let's say the second wave looks like this. When I add them together, what's going to happen? Well, the trough here lines up with the trough here. So yeah, let's pretend it does, yes. And the peak here lines up with the peak here. And so what's going to happen? The peaks are going to add up, right? And I'm going to get a bigger wave. So now, what if instead of lining up, what if they sort of anti-align? So let's see if I can draw this. So that the trough here lines up with the peak of the second one. What's going to happen when I add these two waves together? Yeah, they're going to cancel each other out because the trough is lined up with the peak, and so they're just going to cancel each other out. And so this is what we call constructive interference. And this is what we call destructive interference. And so we can actually see, well, I guess I should say we can actually hear this, okay? So what I have here is sort of a weird trombone. And when I turn this on, I'm going to turn it on just for a second and turn it off because it's kind of annoying. This thing generates a sound, and the sound waves go down this pipe, and go up this pipe, okay? And what I can do is I can change the length of this pipe by pulling on this. And so as I change the length of the pipe, I change how the waves coming from this side and this side line up. And so let's see what happens as that goes. So as I pull this up, what do you notice happening? It's softer, right? And this is a case when we have destructive interference. And so if I keep going up, you can hear it again, right? And so this is when we have the case of constructive interference. All right. And so this is sort of truly a wave phenomenon, right? We don't see this if you're getting hit with baseballs, this constructive and destructive interference. So now let's go back and let's think again about what's happening with these speakers, okay? And I have a demo here, or sort of a model of the situation there. Let me turn this around. So what this is, these are to represent the sound waves coming out from the two speakers, okay? And if you're sitting sort of right in the middle, you can sort of see that the waves line up together. So right here, what do we have? Constructive or destructive interference? Constructive, right? And so now if I shift over a little bit, you notice that this peak lines up with this trough. And so what do we have here? Destructive, right? And so if I keep going a little further, we have constructive interference again, and I keep going a little further. Oh, this thing breaks. But we have destructive interference again, right? Okay. I'll just leave that. So let's go back to this thing again, and let's see if we can actually see that happening. So I'm going to turn on one speaker, and I'm going to turn on the second speaker. And I want you guys to, again, raise your hands if you hear it getting louder. Yeah, so we can sort of see it. There are patches where people can hear it louder. And so now let's do it one more time. Raise your hand if you hear it get quieter. Yeah, and what you guys will notice is there's actually a large patch of you on the end. On the end, we have sort of the walls here that are reflecting the waves, so that it doesn't quite work as well on the end. But I think you guys sort of see this happening, right? So this interference is really, it's happening. And it may be a little surprising, right? Because you think if you add two things together, you can make it bigger. But sometimes you can actually make it smaller. Okay. So let me just make sure I'm not forgetting anything. And oh yeah, so now you guys. So is anyone here planning to go to the Bridge School benefit concert next weekend? No one knows what it is. Well, so imagine you're going to a concert, and it's a pretty big lineup. Neil Young always plays, and this year it's Tom Waits is actually playing. Anyway, so imagine you're at a concert, and you're sort of sitting in the audience, and there are these speakers here. What if you were sitting in a place where this destructive interference happened, and you sort of couldn't hear the music? Can that actually happen? Like, do you see that happening if you go to a music hall? No, right? And so there's a lot of reasons why that doesn't happen. But part of the reason is that sound engineers spend a lot of time thinking about how to place speakers in order to help stop this from happening. Of course, even if they didn't think about it, you wouldn't get complete interference. Like, you wouldn't be able to not hear all the sounds. And so I'm running a little bit behind, so I don't want to get into too many details. So I'll leave this for discussion. If you guys are curious, you can ask your GSIs about this. And so as a GSI, I know I love it when my students come to me with questions. So here's sort of something that you can go to your GSIs and ask about, why you don't see this destructive interference in concert halls and how they prevent it. Okay, so let's go on. So we've just been talking about two waves interfering with each other, right? We can also have this phenomena happen with just one wave. One wave can interfere with itself. And so to sort of understand how this can happen, so if I send a pulse down this rope here, so you sort of see it it moves down, it hits the end, and it reflects, and it comes back, right? And so what can happen is the reflected wave can interfere with the original wave, right? So if this keeps on oscillating, the pulses can just start to interfere with each other, right? And this is actually how musical instruments are designed. They make use of this fact to play different notes. And so what happens is you can, let's see if I can do this. Because of this interference, some of the waves that you send on the rope interfere destructively, and some of them interfere constructively. And so it ends up that only certain kinds of waves can sort of appear on this rope and constructively interfere and sort of reinforce themselves. And so I'm going to see if I can try to get some of these to come up. So here's one, right? It maybe doesn't look too much like a wave, but you can sort of see, and I'm going to draw it on the board to help make it clear. But I can also do something else like this, if you guys can. Is that? This is a lot harder than Bob makes it look. OK, there we go. Right? And then I can do another one like this. All right. So I'm going to need to watch out for these demos. OK, I'm going to draw this on the board here so you guys can maybe see it a little better. I'll do it for here. OK, so what we saw was something like this, where the rope went up and down like this, right? And then another one we saw, the rope went like this, and like this, right? So there was sort of a node in the center that wasn't moving, right? Did you guys see that? And another one looked like this, okay? And if you guys noticed, it was really easy for me to get this one, right? I didn't have to work very hard to get this one. But this one was, it was a little harder, but I was able to get it, right? And when I started going higher to more of these little patterns on the rope, it got harder and harder, right? And so does anybody here, how many of you guys play the guitar? How many of you guys know people who play the guitar? OK. So I think when I'm talking about this stuff, I'm actually going to use the example of a guitar a lot. And this is an optional homework. I want you guys to go home and either play around with your guitar or find somebody with a guitar to play around with so you can kind of see some of the stuff happening. OK, so imagine that this is now a guitar string. And when you pluck it, it's going to vibrate like this, right? It's similar to this rope. It can only have certain waves that can constructively interfere on it. And so because this is the easiest one, this is the one that's sort of the loudest. It's the one that with the greatest amplitude. And this is actually the note that you hear. It corresponds to the frequency of this wave, OK? So this is the note you hear. And so if you want to change the note you hear, what do you do? And how do you do that? Yeah, so you press down on the fret, and what does that do? It changes the length of the string, right? And by changing the length of the string, we have this this property here. When we change the length, we change the wavelength. But the wave speed on the string stays the same. So that changes the frequency. And the frequency is what we hear. Okay, so if you make the wavelength shorter, you increase the frequency. And increasing the frequency, what does that do? Right. And so that was a guitar string. And what I have here is a pipe organ. And it works on a very similar principle. So if you see, what is this? So here we have a C, right? And so if I play this note, you can sort of hear it, right? What happens if I play this one that's shorter? It's going to be a higher note. And as I keep going to shorter and shorter lengths, the note gets higher, right? And what I have here is one that I can change the length on with this sort of stopper. All right, so you get the idea, right? The length here is what determines the frequency, right? And it's because the waves interfere with each other in such a way that this is the loudest wave that you hear on the string or in the pipe organ. And so actually, human hearing sort of starts down at 100 hertz and kind of goes up to maybe 20,000 hertz. But as you get older, your hearing sort of drops down, so you can't hear as high frequencies. And so what I have here is I only went up to so high with the pipe organ, but I have this set of bars that go to even higher frequencies. And I'm not sure if you guys will be able to hear this, so maybe the people in the front will have to tell people what's happening. But so I'm just going to keep going to higher and higher frequencies. And I want you guys to raise your hand if you can hear it. Okay? So that's 4,000 hertz. That's 5,000 hertz. 6,000 hertz. 8,000 hertz. 10,000 hertz. You maybe didn't hear that one. 12,000 hertz. That's 16,000 hertz. Sorry, this didn't. Let's try that one more time. Okay. There we go. Can you still hear that? This is 20,000 hertz. So there's maybe a few people that can hear it. This is 24. No. So you can sort of, I stopped hearing it. I couldn't really hear the 16,000 hertz. And so as you get older, the frequency, the highest frequency you can hear sort of drops. And actually there's a company in oh yeah.
How frequent are dog whistles?
I think it's somewhere around this range, around 20,000 hertz, but I'm not sure exactly.
So it's like a higher ability to hear?
Yeah, they can hear higher frequencies than us. And a similar thing, there's a company in England that produces this device that's meant to sort of disperse teenagers. So if you're like at a gas station or a fast food restaurant and you have a whole bunch of teenagers hanging out causing trouble, you turn this thing on and it blows a frequency at 16 kilohertz or 16,000 hertz, and it's so annoying to the teenagers that they have to leave. And so it's set at 16 kilohertz because 90% of people under 20 can hear that frequency, but 90% of people over 20 can't hear that frequency. So,
What about like little kids then?
yeah, so,
Are little kids going to hear?
yeah, I'm not actually sure if you develop your hearing and then it goes down, or if it starts out. That's a good question, though. I'm not sure about that. Yeah, it's a pretty. And another interesting thing, which I won't talk about, is sort of how you know which direction sounds come from, and that's actually a really interesting topic to think about. But okay, so let's keep going. So yeah, let's get back to the guitar. When I was talking about the guitar, I told you this was the note you hear, right? But all these other waves are still present on the guitar string. So what do? So they actually control the timbre of the sound. So this is why if you play an oboe at a C, or a guitar, or a trombone, or a violin, they all sound different even though they're playing the same notes. They sort of have this same wave on them, but then they also have different amounts of these other waves that appear. And that changes sort of the quality of the sound that we hear. Okay, and so one other thing, going again back to the guitar, I can actually, so if I'm playing my guitar string, say I'm playing my E string and I pluck it, I get this note and I get this wave and I hear an E, right? But I can actually stop this wave from happening on the string. And how do I do that? So I can just place my finger, just rest it on the center of the string, right, which is right at the 12th fret. So if I rest my finger on the 12th fret of the string and pluck it, I'm preventing. So in this wave, the center is moving up and down the most, right? So if I place my finger on it, I'm stopping it from moving. And so if you notice in this one, the center isn't moving at all. So this is actually the wave I hear. And so if you guys do this, those of you that play guitar, you know that when you do this and you pluck it, you hear the octave, right? So what's happening is I'm hearing a note with half the wavelength, so twice the frequency. And that's how we define octaves in our major scale. If we have twice the frequency, then we say it's an octave higher. And so people also use this effect rather than putting it on the center string, or on the center of the string at the 12th fret. You might put it down at the 5th fret and the 7th fret, and you sort of see a similar thing, right? If you just rest your finger on these frets and you pluck the string, you hear a note, right? But it's a much higher frequency. And so what you're doing is you're listening to maybe this one or the one with more pulses on it, right? And why do people do that? You see guitar players do this all the time before they start playing, right? Why do they do that? Yeah, they do it to tune the guitar, right? Yeah, and so you use the word harmonic, right? And that's what these things are called. All these different waves are called harmonics of this fundamental frequency. And so that's why whenever you put your finger down on a guitar string and pluck it, you say you're playing a harmonic. And so when you're doing this, you use harmonics in such a way that the two guitar strings play the same note, okay? And if you play them together, so what I have here are two tuning forks, and they're tuned to the same note. And so when I play one, you can hear this, right? I play the other one. Do you guys think that's the same note? Okay. And so now I can also change the note of the tuning fork by adding a little weight to it. Did that change the frequency? So maybe some people might have perfect pitch and they might be able to tell the difference, but most of us, so I definitely can't tell the difference. They both sound the same to me, right? And so when you're doing this, how do you actually tune the guitar? You don't play one string and then stop it and play the other. What do? You play them together, right? So now when I play this one and this one, what do you hear? Yeah, you hear this sort of beating sound, right? And when you hear that beating sound, what does that tell you about the tuning of these two notes? They're different, right? It doesn't tell you that this one is the right note and this one is the wrong note. It just tells you that they're different. Okay. And so I can change the frequency even more by pulling this up higher. And what do you guys notice? The beating that you heard, the frequency went higher, right? You heard more beats per second. And if I go too far, then you'll start to recognize them as different notes, and you'll hear dissonance, right? But so what I want to focus on is this beating phenomena to try to understand why it happens. And so to understand that, it goes back to, I bet you guys can guess what it involves. What we've been talking about for this whole class so far, right? Interference. So here I'm playing two guitar strings over here that I want to be the same note, okay? But imagine they're not exactly the same note. They're a little bit different. So here is one, and this one is maybe a little bit longer in wavelength. So it's a little bit lower in frequency. And so I'm playing it, and then I keep going along, and so what I'm plotting is sort of the time as I'm listening to this. After some time, what's going to happen is that these two, because this one is a little bit shorter than this one, they're going to the peaks are going to shift relative to each other, right? And so this one is going to move ahead of this one. And what you're going to find out is eventually you're going to get them to line up destructively, right? And then after some more time later, this peak is going to continue to shift ahead relative to this one, and eventually this trough is going to line up again with this trough. And so you're going to get constructive interference. And so this is actually what these beats are. You're hearing oscillations between constructive and destructive interference. Okay, so this is useful. It's useful in telling us differences between frequencies, but it's not useful in telling us what the particular frequency is, right? So that's why when you're tuning a guitar, you always need to tune it relative to a tuning fork or a tuner. And this is also why when orchestras tune, they have the oboe, right? The oboe plays the middle A, I think the middle A or middle C or something, and then everybody tunes to that same note. So you always have to have a reference if you want to use this, because you can only tune relative to something else. Okay, and so now let's get back again to the guitar. So let's say we have our guitar. It's perfectly tuned. So now you have all these strings that are tuned really well. And on a guitar, if you guys know, you have a string at the bottom, or I guess at the top, which is a low E string, and then a string at the bottom, which is a high E string. So they're the same notes, but they're just different octaves. Okay. And so now what happens if I pluck the low E string and then just damp it with my finger? This maybe you might not know unless you've played a guitar or had some experience. What happens? Yeah, so you pluck it and then you stop it, and even though you stop the low E note, the high E string will still be vibrating a little bit, even though you didn't touch it at all. And so I can show you that with this. So I struck this one, right? And when I stop it, if you guys can hear, this one is still vibrating, right? Even though I didn't touch it. And so that's exactly as you said. This is the sort of second idea that I wanted to talk about, which is resonance. That's right. Yes, that's exactly right. I don't know if this will be far enough. They don't maybe have to be exactly the same. If they're close enough, it will work. So I'm gonna just see if this will get us far enough away. Yeah. So let me put this microphone. It doesn't resonate. And actually, so I can show you this demonstration. Sort of gives the same idea. What I have here are three sort of oscillators. They're kind of like upside down pendulums. So I can click hit one and it'll start to vibrate. Okay, and if I hit this one, it'll vibrate, but at a different frequency. And this one is still another frequency, right? So I have these things that can vibrate at three different frequencies, and they're connected by this bar. And this bar is sort of a little bit loose, so it allows waves to travel across the bar to these three oscillators. And when I hit this one, the wave that sends out and goes across is sort of corresponding to the frequency of this thing oscillating, right? Because this is the thing that's causing the wave. So it's sort of vibrating back and forth, and it's causing this bar to vibrate, and that vibration is getting sent across here. And so when I hit this one, what you're going to notice is the one that's sort of the same frequency is vibrating. But they're shaking a little bit, but they're not really shaking nearly as much as this one, right? And so I can do the same thing with this, right? So this one is really going, and these two are maybe kind of going, but not really. And so this gets to the idea. I'm taking energy from here, and I'm transferring it with a wave here. And it's transferring in sort of a kind of peculiar way, right? These three objects sort of have a frequency that they like to vibrate at. And this is what we're going to call the resonance frequency. And when you send a wave to this object at that frequency, then that wave does a really good job of transferring the energy. And you can sort of think of it like if you're pushing a swing, someone on a swing, you want to push them sort of always when they're kind of, at the top of their swing and moving downwards. You don't want to push them this way when they're moving towards you, right? If you did that, you're going to slow them down. And so that's kind of what's happening here. You're pushing them sort of in phase with themselves. And so this idea of resonance is going to get us to what's going to probably be the coolest demo of today. And so what I have here, can you guys see this? Actually, can you guys put this up on the? Yeah. Okay. Great. So what I have here is a beaker, and it's attached. Here is a sound generator, and so it's attached to one of these signal generators that creates an electrical signal, and then an amplifier which makes the signal bigger, and then it goes to a speaker which turns that signal into sound waves, right? And so it's pointed straight at this glass beaker. So now if I play sound waves for this glass beaker, what do you think is going to happen? So if I just play any sound wave, if I just shout at this beaker, what's going to happen? It might vibrate a little, but nothing too surprising, right? But now if I were able to find the resonance frequency, the frequency that this beaker likes to vibrate at, what do you think would happen? Yeah, my wave is going to be able to transfer energy to this beaker really well. And so this beaker is going to get a lot of energy in it, and it's going to vibrate a lot. I'm going to use these earplugs. Well, okay, before I do that, what I'm going to do is I'm going to turn on strobe. Okay, and so the strobe is going to just help us see what the beaker is doing, okay? And now what I'm going to do is I'm going to turn on my... Well, okay, so before I do this, let me ask, I need to know what the resonance frequency of this is if I want to be able to break it, right? How can I figure out what the resonance frequency is? Okay, so if I hit it, what is that going to do? Right, and so I can tell, right, all the other waves sort of don't vibrate as loudly, except for the resonance one. And so by hitting it, I can tell which frequency this thing likes to vibrate at, right? And so now if I send a sound wave at that frequency, that's its resonance frequency. Okay, so what I'm going to do is I'm going to first send in waves below it, and then above it, and then I'm going to send it in at the resonance frequency, and we're going to see what happens, okay? All right, so what happened? Nothing. And so we can sort of see, right, that frequency I sent was lower, right? Okay, so now let's try a higher frequency. Okay. This thing is not actually that loud. Okay. All right, so it vibrated a little bit, right, because I turned it up pretty loud. But still nothing, right? And the speaker actually rotated a little bit. Okay, so now let's get it right at this frequency. And let's see what happens. Okay. All right. I'm just going to turn this over a little because you actually have to hit it right at the right place for this to happen. All right. So you guys saw, right? It really has to be right at this resonance frequency, and when it does, it's really dramatic, right? What happens? You could see this thing vibrating, right? Okay, and actually, this resonance phenomenon, if anybody's heard of the Tacoma Narrows bridge, it collapsed, and it collapsed because of this resonance. The wind caused the bridge to vibrate at a certain frequency, and this caused it to collapse. And if I have time at the end, I will show you the video of this bridge collapsing. But if not, you guys can go on YouTube and see it happening. It's pretty dramatic. Okay, so let's make sure I got that. Yeah. So what I'd like to do now is change directions a little bit. So we've been talking. Oh, yeah. Oh, I'm sorry. Yes. Oh, no, this one. Okay. Yeah, so we've been talking about interference and sort of implications of interference for most of the class so far. What I'd like to do now is to sort of change directions and talk about refraction, okay? And in order to think about refraction, I want us to think about, at the beginning of last class when Bob was sort of introducing waves, he showed you guys a picture of a surfer, right? Raise your hands if you surf or have surfed before. Yeah. So I've tried a few times, not very successfully. But you guys know that, does anybody know what Mavericks is? Yeah. What? Yeah, so it's a big surfing competition that happens kind of like right near, south of San Francisco, kind of near Santa Cruz. Yeah, just north of Half Moon Bay. That's right. And so why does a surfing competition happen there? Why is this such a great place? The waves get really big, right? And so what I'd like for us to do today is see if we can understand why that happens. Okay. And so let me draw a picture of this if I can. So if we go up this way, we get to San Francisco. This is Half Moon Bay. And right here is where the Mavericks Reef is. It's sort of right here, okay? And this is where this big surfing competition happens. It's because it's where we get all these giant waves, okay? And so there are really two reasons why the waves are big here. One of them is because sort of the shape of the coast here, as waves come in, they sort of get reflected and they get focused here, okay? So that's one of the reasons why the waves here are so big. The waves that are coming in from all directions sort of reflect off the coast here and come here, and they get sort of focused together. So the first reason is reflected waves get focused. And now the second reason is the one that I want to talk about. And can you guys guess what that is? You probably can because I told you, right? Refraction. Okay, and to understand how that works, I want to remind you guys a little bit of what refraction is. And I'm going to do this using the model I learned whenever I was in school and people were telling me about this. And in order to give you just a little bit of context about this, I'll tell you I grew up in Oklahoma, and I grew up in Oklahoma City where it's just like one giant suburb, okay? So as you can imagine, people in the suburbs like this, they have very large lawns, and they love to upkeep their lawns, okay? And so this is kind of the context behind the model I'm going to give you. And before I give you the model, I'm going to put a really big disclaimer up front. This is a really bad model for a wave that I'm about to tell you. It's useful in understanding what refraction is and how the waves bend, but it's a really bad model for anything else. So I want you to sort of think about this only for refraction and forget about it for everything else, okay? Okay, so, and as we go through, I'll sort of point out why it's a bad model. Actually, I'll go down here. Okay, so my model is, here I am with a lawnmower, okay? I'm mowing the lawn. So here's my lawnmower. Here's sort of the bag that's holding all my cut grass in it. Here's the motor. And here's me from top down mowing the lawn, okay? And so I'm mowing the lawn. I'm in the grass right now. This is the grass. And here's the edge of the grass, and here's where the sidewalk begins. Okay? And so one thing, if you guys have ever mowed a lawn, you know that pushing a lawnmower in grass is a lot harder than pushing it on the sidewalk, right? So if I'm going in the grass, I'm going a lot slower than I am on the sidewalk, okay? But now, so let's say I'm mowing the lawn, I'm moving along, and so my two hands are the wheels, or the front wheels, and say I'm heading straight towards the sidewalk, okay? I'm heading straight towards the sidewalk, like this. And so I'm in the grass, so I'm moving kind of slow. And then what's going to happen as soon as I get to the sidewalk? I'm going to go faster, right? But my wheels are going to sort of kick up onto the sidewalk, and I'm just going to start going faster, right? And so I want you guys to think of this lawnmower as a wave. And why is this a bad model of waves? Okay. That's true. Is there another reason why? They don't oscillate. So in my model here, I have the lawnmower is actually moving across the lawn, right? There's something physical object that's actually moving across the lawn. But in a wave, do we have that? No. All the pieces of the medium in the wave sort of stay where they are, right? And this disturbance is the thing that travels through. So this is sort of the real main reason why this is a bad model. I have something that's physically moving across that I'm trying to use to represent the wave. But it is useful, as you guys will see, to understand refraction, which is why I'm telling it to you. Okay, so as I'm going straight along, right, you guys told me I'm going to jump onto the sidewalk and start moving faster, right? So if I go straight, I'm just going to keep going straight, right? But now what's going to happen if I come in at an angle? So say I'm down here, and I'm driving along towards the sidewalk. I'm mowing my lawn towards the sidewalk, and I'm going really slow, I'm going really slow, I'm going really slow. And then all of a sudden, this wheel gets to the sidewalk. What's going to happen? It's going to hop onto the sidewalk, and it's going to start moving faster, right? This wheel is going to start moving faster while this wheel is still moving slow. So what's going to happen to the lawnmower? It's going to start to turn, right? But this is still moving forward a little bit. So eventually, this is going to get up onto the sidewalk, and then I'm going to get going straight again, right? Because both wheels are moving at the same speed. So what's effectively happened is I'm moving towards here slowly, and then I get turned and start moving faster, right? So I move towards the sidewalk, and then my wave gets bent, right? Okay. And so this is just to demonstrate a point of refraction. Refraction is whenever you have a wave bend, and it bends because you're traveling. The wave is going from a medium that has a slower, or from either a slower or faster wave speed to basically there's a change in wave speed, okay? And the wave will bend towards the medium with a slower wave speed, okay? And maybe I'll take a minute here to do an aside. What does the wave speed depend on? Well, we talked about here, we had this relationship, right? The wavelength times the frequency is the wave speed, right? But so, for example, in a sound wave, if I change the frequency of the sound wave, is the wave speed going to change? No. What's going to change? The wavelength, right? So the wave speed is really a characteristic of the medium the wave is traveling through, right? And you can think about it like this, because the wave is traveling through the medium and it's causing disturbances in the medium, right? And so the speed at which the medium can move sort of limits how fast the wave can travel, right? Because we have to be able to transmit the information of this thing moving from here to the one next to it, to the one next to it, and so on, right? So the wave speed is something that really depends on the medium. And so, for example, if I have this rope and I make it tighter, what's going to happen to the wave speed? It's going to increase. Why is that? Well, so when I make this rope tighter, the little pieces of rope inside it are stretched farther, right? And so they're pulling on each other harder. And so whenever one piece goes up, it causes the one next to it to go up even faster because it's a greater force, right? So when I increase the tension in this rope, the wave speed is going to increase. And now what if instead of increasing the tension, I just got a heavier rope? I made this rope much thicker and kept the same tension. What would happen? What would happen to the wave speed? It would slow down, right? Because if the rope is heavier, it takes more force to move it, right? Because it has more inertia, right? And so it's harder to move each piece of the rope. And so that's going to slow down the wave. And what about with sound waves? If we have a sound wave, it's a pressure wave moving through the air. What affects the speed of the sound wave? Yeah, so it's really the temperature of the air, because the temperature of the air tells us how fast the particles in the air are moving, right? It's a measure of the kinetic energy of the air. So if we increase the temperature, these airs the particles in the air are moving faster and faster, right? And if they're moving faster, then they can sort of transmit their energy better, or sort of more quickly across, right? I guess my point of all this is the wave speed is really depending on the medium, not on the wave itself. So what if I took a pulse on this rope, a small pulse? Actually, I should probably... So if I take a small pulse, you can sort of roughly see how fast it's going. It may be a little bit too fast to time. But now if I make a big pulse, you can see it's still roughly moving at the same speed, right? So the amplitude of the wave doesn't affect the speed. It's really the string, or the medium the wave is moving through, that does. Okay. I forgot where I was. We were talking about refraction, right? So we have this wave bending, and it bends in the medium with the slower wave speed. It bends towards the medium with the slower wave speed, right? And this lawnmower analogy is meant to help you remember that, with the caveat that this is not a very good model for a wave, okay? And so what does this have to do with Mavericks? Well, here's my picture. Before I go to that, let's say here I drew a sort of a straight line between the two medium, the slow and the fast medium. What if I have a curved line, and I have a wave coming in? And so what I'm drawing here are the fronts of the wave. The places in the wave where there's a peak, okay? So what's going to happen to this wave as it moves into this, where this is a faster media, and this is a slow one? What's going to happen to the wave? It's going to bend, right? So when the wave as soon as the wave gets to this point, this part is going to slow down, but these two, the ends are going to be able to be moving faster, right? And so they're going to sort of move faster until they get here, and it's actually going to cause the wave to bend, okay? And so it's going to cause a wave to bend and focus in. And this is actually how lenses work, okay? So we know light is also a wave, and so my eyeglasses are curved so that they can do this to light waves. They can sort of bend them and focus them towards my eye. And so now the reason why this is relevant to Mavericks is there's a second reef at Mavericks that's sort of farther out the coast. And what it does effectively is it slows down waves that reach it. So it's a slower medium for the waves, the water waves that reach it. So what's that going to do to these water waves that are coming in? It's going to bend them inwards, and it's going to focus them right to this point here. So we're taking all the energy of this really long wave across, across this whole region of the ocean, and we're focusing it down into just a little part. And so what that's doing is it's concentrating the energy of that wave into this little part. And so that's how the amplitude gets bigger. Okay, so I want to maybe give one more example of where we see refraction, and then I'll do a summary, and then we'll be done, okay? So have any of you guys seen or heard about a mirage, or what is a mirage? Has anybody seen this? Yeah, what happens? Yeah, so you're in the desert, really hot, or you're driving down the road, and you see water ahead of you, and when you get there, it looks like it's not there. It's not there, and it looks like it's still further ahead of you, right? And so here, I can go here. So let's try to understand how refraction, or what refraction has to do with that. And before we do that, let's try to get a sense of why, when we see water, it sort of looks kind of bluish and like, let's try to understand why that is. Because if you just take a cup of water, it doesn't look like that, right? It has, you have to be looking at like a body of water for it to look like this. So here I am, and here's the ground, and let's say the water starts right here. Can you guys see this? Is this thing in the way? Oh, let me turn this. Can you guys see this? Yeah, okay. So when I look at the water, my eyes are sort of pointed this way. And whatever light is coming from this direction is what my eyes think the water is, right? Right, because I'm looking in that way. Whatever light's coming back at me is what I'm guessing the water is. And so what I'm actually seeing is light coming in from the, I'm going to write through our announcements a little bit. Light coming from the sky, and it's hitting the surface of the water, and it's reflecting and coming to my eye. So really what I'm seeing when I look at water is the sky, a reflection of the sky, okay? And so now, what I'm going to do is I'm going to take away the water, because when we have a mirage, it's that there isn't actually water, right? So there's no more water here. This is all just the pavement of the highway or something. And what's the other condition that we need in order to have a mirage? We need it to be a hot day, right? And so when it's really hot, what happens to the pavement? It gets really hot, right? And so the pavement, it's black. It's absorbing heat from the sun, and it's sort of releasing it out a little bit through the air. And so what's happening is just near if you're touching the pavement, it's really, really hot, right? And if you're just above the pavement, it's still pretty hot, but it's not as hot. So this is really hot. And then if you're a little higher, it's still, sorry. This is really hot. And if you're higher, it's still hot, but it's not as hot. And as you go higher, it's somewhat hot. And so on and so forth, right? But right near the surface of this pavement, it's really, really hot, okay? And so now if I'm looking down this way, what am I going to see? Or maybe a better question is, what's going to happen to the light from the sky that I drew here? It's going to come in, And what happens to the wave speed of light when the air gets hot? It increases, right? And this maybe, you can think of this as because when the air is hot, it gets sort of less dense, right? There's less air, and that's kind of how you can think about how this happens. But the bottom line is the wave speed of light changes, and it goes faster when the air is hotter, okay? And so what happens to this ray of light that's coming in? Remember, this is a slow wave speed medium, and this is a fast wave speed medium. So what's going to happen to the light wave? Right, just like my lawnmower, it's going to bend towards the slow medium. So it's going to come in, and it's going to bend towards the slow medium, and it's going to come out to my eye. And so again, when this situation happens, I'm just still looking at the sky again. It's just that rather than being reflected off the surface of water, it's being refracted, and the light is being bent to my eye. And so in the textbook, you guys have read that there are these sound channels in the ocean and in the sky that rely on this principle, right? And this is how whales communicate and all that. And another interesting thing is this is also how fiber optic cables work. And I think you guys will talk about this next week when we talk about light. But this idea of light getting bent towards the slower medium is how you get light to follow a fiber optic cable. Okay. So are there any questions about this or about anything? Oh, yeah.
Can we watch the first video?
Yeah, so let me just give my quick summary, and then I'll ask them to put it up while right at the end of class, okay? Was there another question? Yeah.
If you had two waves that were the exact same frequency, but you started one wave and then you started the second wave halfway through the period of the first wave, would they completely?
Yeah.
Or would they eventually work out?
So if they're the exact same wave and you've just started it half a phase away, then yeah, they will completely cancel out. And this is exactly how noise canceling headphones work. The headphone listens to what's coming in towards your ear, and it makes a sound that's with the wave is just out of phase of what's coming in, and so the two waves cancel out. Yeah. Yeah, that's right. So you sort of hear it getting louder and softer. And so the louder part is constructive and the softer part is destructive. Okay. So I'm gonna just make sure I tried to word this very carefully, so I want to use the words I wrote down. So we really talked about three main phenomena. So what was the first one? Interference, right? Well, let me just write this. Okay, and so what is interference? It's the fact that when you have waves, they can add together and reinforce themselves, but they can also add together and cancel each other out. And so this is sort of a really sort of wave phenomenon. You don't see this when you have a bunch of particles hitting you, right? The energy always adds up. What was the other one that we talked about? Resonance, yeah. Oh, you guys can just look at our agenda, right? And you know the answer. And what is resonance? Resonance is the fact that we have objects tend to like certain frequencies. And if your wave matches that frequency, it can transfer energy to that object really well. Right, and we saw that with the beaker here. And what was the last? Refraction, right. And what is refraction? Refraction. That looks like, sorry. Okay, refraction. What is refraction? Yeah, exactly. Waves bend towards slower media, or slower wave speed media. I'm just going to put quotes around the slower because I mean slower wave speed. Okay, so these are the three phenomena that we talked about. And we have just like a couple of minutes left, so maybe can I ask to get the video of the bridge